In this session, we will solve these control problems. So, the first example, an ideal PID controller. So, it is a PID controller. The transfer function is 1 plus 1 divided by 0.5 s plus 0.2 s. We have to find out the frequency at which amplitude ratio is equal to 1. So, you see, if we have the transfer function as Kc 1 plus 1 by tau is plus tau ds, so g of j omega is Kc 1 plus j tau d omega minus 1 by tau I omega, right. So, amplitude ratio is mod of g j omega is under root of 1 plus tau d omega minus 1 by tau I omega square. So, obviously, tau d omega minus 1 by tau I omega multiplied by Kc must be equal to, or this should be 0, right. Then here for this problem Kc equal to 1 and we will have the amplitude ratio equal to 1. So, omega is equal to 1 divided by under root of tau d tau I. Now, what is tau I? 0.5. What is tau d? 0.2. So, answer is 0.5 into 0.2. Next, a process, okay, not this one. Okay. The time constant of a unit gain first order process plus a dead time. So, unit gain 1 e to the power minus tau ds divided by tau ps plus 1. So, according to the statement, the time constant of a unit gain first order process plus a dead time is 5 minutes. So, tau p is equal to 5 minutes. If the process lag at a frequency of 0.2 radian per minute is 60 degree. So, phi at omega is equal to 0.2 rad per minute is minus pi by 3, right, because the lag is 60 degree. So, phase shift is minus of 60 degree, which is minus of pi by 3. Then the dead time in minute. Now, you see we have to calculate here what is the dead time. So, this is actually g equal to e to the power minus tau ds and 1 divided by tau ps or 5s plus 1. And this is in minute. So, amplitude ratio, no, the phase shift amplitude ratio we do not have to calculate. The phase shift phi is phi of, this is say g1, this is g2, the entire transfer function, right. So, phi 1 plus phi 2. Now, for a dead time element, the phase shift is minus of tau d omega plus tan inverse of minus tau p, which is 5 into omega, and that is equal to minus pi by 3. So we can write that minus pi by 3, or rather this tau d omega is equal to pi by 3 plus tan inverse of minus 5 omega. So this is tau d into omega is 0.2 pi by 3 plus tan inverse minus 5 into 0.2. So you can calculate that when we can solve tau d in minute, right? So that's the understanding that for a multi-capacity process, the phase shifts are to be added, whereas amplitude ratio it is to be multiplied. So the next, the Nyquist plot of a first order system coupled with a pure dead time. This we have already discussed. See, we have to draw there are options and we have to finally select which one is the Nyquist plot of a first order system coupled with a dead time. So you see that G, if we consider as Kp into e to the power minus tau ds divided by tau ps plus 1, amplitude ratio becomes Kp into 1 divided by tau square tau p square omega square plus 1 multiplied by 1, because the dead time has got an amplitude ratio equal to 1. And phi, as we have solved in the previous problem, is minus of tau d omega plus this tan inverse of minus tau p omega. Now you see what we are doing. This is for a first order. This will start from Kc comma 0 at omega equal to 0 and approach to this origin when omega tending to infinity from minus 90 degree. And for a dead time, the amplitude ratio is 1. So it is like this. So here what will happen if we combine these two? See, the amplitude ratio at omega equal to 0 is Kp, amplitude ratio omega tending to infinity, it is 0, right? And here phi at omega equal to 0 is 0 and phi omega tending to infinity is minus infinity, right? So what means that it will go on circling and finally will converge to the center, right? So if we add this, we will get this sort of profile. So this is omega 0 and at the center we will have omega equal to infinity. Next, given below a simplified block diagram of a feed-forward control system. So this is a gate problem actually. DS, this feed-forward control system. Here we have GD. GP, GF, it goes here, and finally produces the output Y. Right. The transfer function of the process GP is 5 divided by S plus 1, and the disturbance transfer function GD is 1 divided by S square plus 2S plus 1, the appropriate choice of GF. Right. So, you see that this is not a typical feed forward control system for which the block diagram we have studied, and we have got the controller transfer function. Here we have to understand the logic. What is the logic? How D is linked to Y, right. So, that we have to calculate, and from there, irrespective of any, as there is no set point, irrespective of any variation in the disturbance, we have to keep this Y bar always at its set point. So, Y bar is equal to D into GD plus D into GF into GP, right. So, D within bracket GD plus GF into GP, and what we have to keep here, these are all deviation variables. So, Y prime or Y bar must be equal to 0 irrespective of any change in this D. So, Y is equal to 0 for, or even for ds not equal to 0, which means GF is equal to minus of GD by GP. Now, GD is 1 divided by S square plus 2S plus 1, total divided by 5 divided by S plus 1 with a minus sign. So, here it will be 1 divided by 5 into S plus 1 with a minus sign. So, it is option B, right, it is option B. So, what is important to note here, we should not use the feed forward formula of GSP or GC directly. We have to use the block diagram, we should write this Y and D relation, and therefrom we must understand the logic of this feed forward entire loop, that as it is typically a servo mode of control, we do not have any set point. So, disturbance must not affect this Y. So, Y or the deviation of Y must be always 0. So, Y and D's transfer function, the intermediate transfer function, which is this block itself, must be 0. Okay. Now, this problem is, we have a block diagram. Let us write that. RS, here this is a block with Km is equal to 1.5, then it goes to the comparator, this is Kc, this is 0.5, which is Gv, that is the valve basically. Next it goes to Gp, it's minus 2 by S, pure capacitive process. Next, adder block, here the disturbance block is also having minus 2 by S, here it is D prime, or rather capital D, S, producing Y, right, or C, sorry, here it is Cs, and Gm is equal to 2. Right, so that's the block diagram given in the system. A P controller is being used with Kc equal to minus 4. So Kc is minus 4, this is Gc. If a step change in the disturbance of magnitude 2 is introduced, here we introduce a step change of magnitude 2, right. Disturbance of magnitude 2 affects the system, then the value of the offset is, we have to calculate the offset here. So it is a regulatory problem, and so let's simplify this, okay. And the regulatory block, how it will affect, let's simplify. So R into Km is the signal here, right, minus 2 into C is the signal here, 2 into C, right. It is subtracted, multiplied by Kc into 0.5 into minus of 2 by S plus D into minus of 2 by S is equal to C. So, for the disturbance block, C by D or C by D we can write as minus of 2 by S, denominator will be this this part, and C is going to this side. So, it is 1 plus 2 Kc into 0.5 into minus of 2 by S. Okay. So, we are considering only the regulatory block. So, it is minus of 2 by S divided by 1 minus this 2 into 0.5, that is 1. So, minus 2 Kc divided by S. So, that is our transfer function. So, we have introduced this D as 2 by S. Okay. So, what is the offset? Offset is the desired change of the C, which must be 0 because we are changing the disturbance, minus this actual C, minus this actual C, that is C at infinity. So, which from the final value theorem is limit S tending to 0, S into C bar S. So, minus limit S tending to 0, S minus 2 by S divided by 1 minus 2 Kc by S, into 2 by S. That will be my answer. So, this minus and this minus cancels out, giving plus, and this S cancels out, this S cancels out, giving an S here. So, S is 0, right, S is tending to 0, so it is 2 divided by minus of 2 Kc. So, minus of 1 by Kc, and Kc value is equal to minus of 4, so it is plus 1 by 4. So, that is 0.25, So, there is some error. Okay, this 2 is there, right. So, I have done some mistake here. So, this 2, so it is 2 by Kc, it is 4, and here this goes to 0. So, it is minus of 2 Kc. So, 2 cancels out. So, 2 by Kc and Kc is 4. So, it is half, and that is 0.5. Option A. Okay. Next question is also a gate question. A unit gain, that is Kp equal to 1, second order, unit gain second order under damped process zeta less than 1 has a period of oscillation of 1 second, right. It has got period of oscillation capital T equal to 1 second, and the decay ratio 0.25, right, and the transfer function of the process. So, you have to calculate the transfer function. So, time period, it is 2 pi divided by this omega, right. So, 2 pi divided by for the second order, the natural, this period of oscillation omega is equal to 1 minus zeta square by tau. So, root over 1 minus zeta square, and numerator there is tau. So, that is T, which is 2 pi tau divided by 1 minus zeta square equal to 1, and decay ratio, it is exponential of minus 2 pi zeta divided by under root of 1 minus zeta square equal to 1 by 4. So, from these two equations, you have to solve for tau and zeta. So, once you know this tau and zeta, the rest is pretty simple. The transfer function will be 1 tau square s square plus 2 tau zeta s plus 1, right. So, from this statement of time period and this decay ratio, we have to solve for tau and zeta, then we substitute and we will get the transfer function. Next, consider following transfer function Gp equal to 5 divided by 2s plus 1 to the power 4, right. Time constant is in second, 2 is in second. We have to calculate the crossover frequency in radian per minute, sorry, radian per second. So, first you see crossover frequency is at omega equal to omega CO, phi equal to minus pi. Right. The phase shift is equal to minus 180 degree. So, here it is 4 first order processes in series. So, phi overall equal to 4 and all are identical. So, naturally we have to go for summation phi 1 plus phi 2 plus phi 3 plus phi 4 and all these phi's are same. So, you can write 4 phi 1, right, and 1 stands for the time constant of the first order process, which has got a transfer function 1 divided by say 2s plus 1. So, phi the gain we can separate out, right. So, this is 4 into tan inverse of minus 2 into omega, because for a first order process the phase shift is tan inverse of minus of tau p omega. So, this is minus pi and minus pi by 4 tan inverse of minus 2 omega, right. So, tan of minus pi by 4, which is minus 1, is minus 2 omega cu. This is omega cu, right. So, omega co is equal to half radian per second. So, answer is 0.5 radian per second. For the computation of Ziegler-Nichols setting, the ultimate period in second per cycle and the ultimate gains are. Now, what is the ultimate period? Pu is equal to 2 pi by omega cu, and ultimate gain Ku is equal to 1 by m, and m is amplitude ratio at crossover frequency. So, Pu is 2 pi divided by half. So, it is typically 4 pi. So, it is typically 4 pi, and amplitude ratio is 5 into 1 divided by under root of tau square omega square plus 1 whole to the power 4, which is 5 divided by tau square omega square plus 1 whole square, right. So, amplitude ratio at omega co is half. So, 5 divided by tau is 2. So, 2 square multiplied by omega square is half, okay. So, 1 divided by 2 square plus 1. So, this gives you 2 and this square. So, 2, this is 1 plus 1 2, 2 square 4. So, it is 5 by 4. So, here Ku becomes 4 by 5 because it is 1 by m, right. So, it is 0.8, 4 by 5, that is 0.8. So, that is the problem. Okay. a characteristic equation, the characteristic equation for a system, characteristic equation s cube plus 9s square plus 26s plus 12 2 plus kc equal to 0. Using the Routh test, the value of kc that will keep the system at on the verge of instability is. So, here what we can see that all the coefficients are positive, right? 1, 9, 26, 12 into 2 plus kc, all these are positive. So, Routh test 1 is passed. So, we have to go for Routh test 2, right. So, there we have to construct the Routh-Hurwitz table. So, this is, you see, it is a0 s cube plus a1 s square plus a2 s plus a3. So, the row 1 is a0 and a2. a0 is 1, a2 is 26, then 0. Row 2, a1 which is 9 and a3 which is 12 into 2 plus kc, right. So, row 3 is 9 into 26 minus 12 into 2 plus kc divided by 9, right. This will be 0, 0, 0. And next R4, this multiplied by this, minus 9 into 0 divided by this. So, it is 12 into 2 plus kc. And after that R5, it is all 0. So, we have to focus on the first column element, and this must be set greater than or equal to 0 for the stability. So, 26 minus 9 minus 12, 2 plus kc must be equal to 0, and from there if we solve the kc, I will get the kc value which will lead the system on the verge of stability, right. So, a linked question is given. What is that? A PID controller output in the time domain is given by Pt is equal to 30 plus 5 into Et plus 1.25 0 to t epsilon t dt plus 15 into d epsilon dt. Sorry, d e dt. Here error is represented as E. So, we can understand that Cs, the bias signal, is 30, Kc is 5, Kc by tau I 1.25, Kc tau d equal to 15, right. So, tau I is equal to 5 divided by 1.25 and tau d is equal to 15 divided by 5, which is 3. So, this is 4, right. Now, the transfer function of the controller has been asked. The first question, the transfer function of the controller. So, controller's transfer function is Kc 1 plus 1 divided by tau is plus tau ds, right. So, Kc is 5, 1 plus 1 divided by tau I is 4s and tau d is 3s. So, this is the transfer function. Next, the transfer function of the process to be controlled. So, this is the first part. Transfer function of the process to be controlled, Gp, is 10 divided by 200s plus 1. the measurement of the controlled variable is instantaneous and accurate. That is GM is equal to 1. And obviously, we will consider GF equal to 1 because nothing else is given, right. So, what is asked? The characteristic equation of the closed loop. So, it is 1 plus GC, GF, GP, GM equal to 0. So, initially we have calculated the controller transfer function is 5, 1 plus 1 divided by 4s plus 3s, right, multiplied by GF, that is 1, GP, which is 10 divided by 200s plus 1 multiplied by 1 equal to 0. So, now you rationalize that and get the exact transfer function. Next question, a tank of cross sectional area, so area is 100 centimeter square, an inlet flow rate Qi in centimeter cube per second, an outlet flow rate Qo, that is also centimeter cube per second, is related to the liquid height H centimeter per second, centimeter. The relation is Q naught equal to 3 under root of H. Then the transfer function H bar S divided by Qi bar S in deviation variable form of the process around the steady state is equal to what? Around the steady state Qis equal to 18 centimeter cube per second, Hs is equal to 36 centimeter. Right. What will be the transfer function? So, we know that the model gives you A dH dt is equal to Qi minus this 3 into under root of H, right. So, this is to be linearized. So, under root of H is under root of Hs plus 1 divided by 2 into under root of Hs into H prime, because this H minus Hs is H prime, right. So, A dH dt is equal to Qi minus 3 under root of Hs plus minus 3 divided by 2 under root of Hs into H prime. So, its steady state equation A dHs dt equal to Qis minus 3 under root of Hs minus 3 divided by 2 under root of Hs into 0, because H prime is 0 at steady state. So, if we subtract, we will get A dH prime dt is equal to Qi prime minus 3 divided by 2 Hs into H prime. So, it is 2A divided by 2A under root of Hs divided by 3, right, into S plus 1 H prime bar is equal to Qi prime bar upon taking Laplace transform and shifting this to this side and dividing the entire equation by 3 divided by 2 root Hs. Okay? And here it should be also multiplied by 2 root Hs divided by 3. So, Hi prime bar divided by Qi prime bar is equal to this 2 under root Hs by 3 divided by 2A under root of Hs divided by 3s plus 1. Now we'll substitute the values. HS is 36, the under root of 36 is 6, and so 2 into 6 by 3 divided by 2. Now area is 100 into 6 by 3 into S plus 1. So here it is 4, denominator this is 2, so 400 S plus 1. So that is the required answer. 4 divided by 400 S plus 1. Okay. So this is another link problem based on frequency response. For a system shown below, what is that? X G1s Y G2s Z. Now G1 is equal to 1 divided by tau 1s plus 1, G2 1 divided by tau 2s plus 1. Both are first order. When the system is excited, this X excited by a sinusoidal input, sine of omega t. The intermediate response Y will be A sine of omega t plus phi, right? Now the first question, if the response Y lags behind the input X by 45 degree, that is phi is equal to minus 45 degree, and tau 1 equal to 1, this is question 1, tau 1 equal to 1, that input frequency will be what? So it's very obvious that it's a first order process, and for which the phi is equal to tan inverse of minus tau 1 omega. So phi is minus 45, that is minus pi by 4, tan inverse of minus omega, right? So tan of minus pi by 4, so this is minus 1 is equal to minus omega, so omega equal to 1, right? Yeah. Next, for the same input, the amplitude of the output Z will be, the amplitude of this output Z will be, tau 1 is 1, yeah. There is a relation given, tau 2 is equal to 2 tau 1. So amplitude of the output, so amplitude ratio is AR1 into AR2. So AR1 is 1 divided by under root tau 1 square omega square plus 1 under root tau 2 square omega square plus 1. And tau 1 we have got 1, right? So tau 2 must be equal to 2. So under root omega square plus 1 into under root 4 omega square plus 1. And for the same input means omega equal to 1. So it is 1 by root 2 into 1 by root 5, right? So it is 1 by root 10. So around 0.32 or something, right. Root 10 will be 3 point something, 3.33 something like that, and 1 by root 10 will be 0.32. Yeah. So these are the answer to two linked questions. Second question, the next question. A unit step input is given to the process that is represented by, so input f prime bar, unit step 1 by s. And the process has got g, which is s plus 2 divided by s plus 5. The initial value t at 0 plus of the response to a step change is. So you are asked that y is equal to y at t equal to 0 plus, and that is limit s tending to infinity s into y prime bar s, right. So limit s tending to infinity s, y prime bar is what? G into f prime bar s. So g is s plus 2 divided by s plus 5 into 1 by s. So it is limit s tending to infinity, if I take s common, so it is 1 plus 2 by s divided by 1 plus 5 by s. So this is simply giving you 1. Yeah. Next, there is a column matching. You see the group 1 element, next problem, group 1 element, Ziegler-Nichols, P, Q is underdamped response, R is feed forward control. And group 2, the elements are first process reaction curve, number 2 decay ratio, number 3 frequency response, number 4 disturbance measurement. So obviously Ziegler-Nichols, this is related to frequency response analysis. Underdamped response is definitely associated to decay ratio, and feed forward control is definitely, it can be done only when we have the measurement of the disturbance, right. Okay. So next we have a block diagram simplification problem. See, R two one by S, two this is R and this is C. Note that in block diagram simplification, we have a very simple rule that if I have a G here or G1 here and G2 here, and here we have plus and minus, this is F, this is Y. So you see that F minus G2Y whole bracket G1 equal to Y. So F into G1 is equal to 1 plus G1 G2 whole Y. So Y by F is equal to G1 divided by 1 plus G1 G2. So naturally we can replace this entire block as a single block, which is 1 by S divided by 1 plus 1 by S. Right. And this again by a simple block 2 divided by 1 plus 2, that is 2 by 3. So now it has been reduced to R, then this comparator, then 2, then 1 divided by S plus 1, then 2 by 3 going to C, and here it goes to R. Sorry, it's minus. So again for this sort it will be product of these 3 divided by closed loop this GOL 1 plus GOL. So C divided by R is equal to 2 1 plus S by 1 into 2 by 3 divided by 1 plus 2 S plus 1 into 2 by 3. Right. So it is 4 divided by 3s plus 1, and numerator is 3s plus 1 plus 4, total divided by 3 into s plus 1. So this cancels out. So we have 4 divided by 3s plus 7. Right. So it is 4 by 7, 3 by s into 7 plus 1, a typical first order system. So next problem, this is a typical example, this here in this one, this is a typical example of block diagram simplification. So if you don't want to use it, go simply by adding and subtracting and assuming any intermediate signal which you don't know, and you will get the same result. What is the question? A PD controller of transfer function PD transfer function GC is equal to 3 1 plus 5.2 S is subjected to an input f prime t, that is 3 plus 2t square. The output at t equal to 0, or rather this is an error signal, E prime t is equal to 0. So C prime t at t equal to 0 plus. Right. So E prime bar S is equal to 3 by S plus 2, then t square. So you see the Laplace transform of t to the power n is equal to n factorial divided by s to the power n plus 1. So here it is 2 divided by s cube. So it is 3 by s plus 4 by s cube. Essentially y prime bar s is equal to 3 1 plus 5.2 s into 3 by s plus 4 by s cube. And we have to solve for what? Y prime at t equal to 0 plus. So which we can apply the initial value theorem s 3 1 plus 5.2 s into 3 by s plus 4 by s cube, right. So this is s and s square. Now we have no further reduction. So okay, yeah, s we can take out. So 3s 1 by s plus 5.2, this will be 3, right, and 4 divided by s to the power 3 by 2. Sorry, s to the s square. So what will happen? This s and here it is limit s tending to infinity. So this s is not going to cancel out. Okay. So what will happen? The overall outcome momentarily it will jump to infinity, because this s is not, if it is 3t, then it would have been different answer, but here for that see actually the physically how we can explain e prime versus t, and this is time t equal to 0, right. So and it is f prime t, e prime t. So initially it is 0, then it is 3, right, this is t equal to 0, and from t y is equal to x square. So it will be like this. And now when it faces this 0, what a d mod will encounter? A derivative which is infinity. At t equal to 0 plus, it will have a derivative which is infinity, right. And because of that, it will give you infinity here. Okay. Because the derivative mode jumps to infinity as its phrase, as simply it phase a hike from 0 to 3. Okay. This is a very interesting problem. A manufacturer of a clinical thermometer claims that his product is a 1-minute thermometer. 1-minute thermometer. What does it mean? That requires only 1 minute contact time to register 2 temperature, which is 98% or greater than equal to 98% of the actual temperature. Right. What is the time constant of the thermometer in second? See, the response of a first order or response of a thermometer T prime T, right, it is A into 1 minus e to the power minus t by tau t, right. A is the step change. So finally its value should be A, and we know that T prime at 4 tau p is equal to 0.98a. So we can say that 4 tau p is nearly equal to 1 minute and tau p equal to 25 seconds approximately, right? So this is a very smart kind of problem formulation, and from there we have to answer the question. So that's all about this session. In the next session we will also continue solving problem, and that will be the last session of process control. Thank you.